We're going to do continuity today. Realize we've got 14 slides to go through here, so let's just get after it. Function is continuous. Informally is if when you graph it, it has no breaks, no holes, no gaps, no jumps. And basically is if you can draw the picture without lifting up your pencil, then the function is continuous. So let's take a look at this. Is this function continuous at x equals 1? Well, here's x equals 1. And so can I draw this picture through x equals 1 without lifting my pencil? And obviously not, because I come this way and I have to go, oh, there's a hole, so jump over here and teleport or whatever. So the answer to that is no. Why is that? Because I had to lift my pencil. What about this function here at x equals 1? X equals 1 is right here, so can I draw my graph through x equals 1 without lifting my pencil? Well, yes I can. So this function is continuous at x equals 1. Now what about over here at x equals 3? We have a vertical asymptote at x equals 3. So can I draw my graph through x equals 3 without lifting my pencil? And that answer is obviously not, because I have to go from down here to negative infinity instantly up here to positive infinity, and I had to lift my pencil to do that. So that answer was no. But this one was yes at 1. Okay. We're going to go through a formal definition now. There are 3 things that have to be true for a function to be continuous, and all 3 of these things have to be true. First of all, f of a has to be defined. Now let me tell you what that means. You have to have a filled-in circle at x equals a. So let's go through these examples and see if f of a is defined. Here's a graph. F of a is the y-coordinate at a, and you see there's a filled-in circle, so yes, f of a is defined. The second graph over here, do we have a filled-in circle at a? Yes, we do. It's right up here, so f of a is defined. The third part is, do I have f of a filled-in circle at a? I do. F of a is defined. This fourth part is the example where f of a is not defined. I don't have a filled-in circle anywhere. So this here, f of a is not defined. So what we're looking at is that enough to guarantee continuity? If I have f of a, if I have a solid dot, does that mean that the function is going to be continuous? Well, here I've got a solid dot at 1. Is this function continuous at 1? Can you draw this graph without lifting up your pencil? And the answer to that is no, because once I get here, I have to bounce down here and put a little dot, and I have to come back up here and do this. So no, that is not enough to determine continuity. Here's another example. I've got f of 1 being defined, but I cannot draw my graph through that point. So anyway, that actually is x equals 2. I messed that up. It should be x equals 1 over here. So anyway, f of a being defined is not enough to determine continuity. So there's a second thing you have to look at, and that is that the limit of f of x as x approaches a must exist. So not only does the function have to be defined there, but we also have to have a limit that's existing. So here I have a limit existing at a, and here I have a limit existing at a. Remember, the y-coordinate from the right has to match the y-coordinate from the left. The y-coordinate from the right has to match the y-coordinate from the left. This is an example here where the limit does not exist. And here, so I have another example of these limits do exist. So let's take a look and see if that's enough to determine continuity. Here I have the limit existing from the left and the right, but is this function continuous? No. So f of a being defined, that is true here for this picture. And the limit, fix that a there, as x approaches a of f of x has to exist. Well, that was also true here. But this function is still not continuous. So I need a third check. There's a third thing I have to know. And that is the limit as x approaches a of f of x and f of a have to be the same number. If that is true, then that is enough to determine continuity. So let's take a look here. This first example is f of a defined. F of a is defined because you have a filled-in circle at a. Does the limit exist? Yes, the limit exists. The limit as x approaches a does exist it would be whatever this y value here is. However, the problem is f of a, this black dot, does not match the open circle where my limit exists. So the only way that happens is in this picture right here. We have f of a existing. We have the limit as x approaches a also existing. And looky there, they're the same number. Okay, so let's take a look here. Is this function continuous at x equals 1? At x equals 1, let's check and see. What is f of 1? Well, f of 1 is negative 2. So we've checked f of a is defined. What about number 2? What is the limit as x approaches 1 of f of x? Well, that limit would be from the left and from the right. That limit is negative 6. So the limit exists. However, that third check is the fact that f of 1 does not equal the limit, because these two numbers are not the same. Therefore, we say for x equals 1, no. Now let's try x equals negative 1. X equals negative 1 is over here. What is f of negative 1? Well, it is negative 2. Number 2. What is the limit as x approaches negative 1 of f of x? So we go to the graph and we look a little to the right and a little to the left, and we see that limit is approaching negative 2. And the third check is these things equal. F of negative 1 is the same number as the limit as x approaches negative 1 of f of x, because we got the same number here. So is it continuous at negative 1? Yes. That's a formal way of saying continuity. The informal way is, well, you didn't have to lift your pencil, ding dong. So therefore it's continuous. But down here you did have to lift your pencil. Okay, what about if I just ask you is something continuous? And it's a function form and not a graph. Well, the first thing you want to do is find f of a. F of a would be 2 squared minus 3, which would be 1. So you have a function is defined at 2. What about the limit as x approaches 2? Well, here we know that we're just supposed to plug it in and see, and make sure we don't get something funky like 0 over 0 or something like that. So we just plug it in, and we get the same thing. F of 2 matches the limit as x approaches 2, so yes. Excited exclamation point, that is continuous. What about this example down here? What is f of a, or f of 3? Well, f of 3 is 3 squared minus 9 over 3 minus 3, and we get 0 over 0. And that is indeterminate. And in this example, f of 3 does not exist. That means you're going to have a hole in your graph. Now, we can still go through here and find the limit as x approaches 3 the way we have been doing by factoring and canceling, and then trying the limit again, and we get that the limit exists. However, f of 3 does not exist, so this function is sad face, not continuous at x equals 3. All right, let's try a piecewise function. Well, first of all, let's find out what is f of a. F of 2 is, well, we got two different equations. Which one do I use? Well, looky here. Let's use the one that's got the or equal to on it. That's the one that we use for f of 2. And if we plug that in, we get 3 times 2 minus 2, which is 4. F of 2 exists. Awesome. Now, what about the limit as x approaches 2? Now, here we're going to have to check two things. We're going to have to check from the left and from the right. Now, if we were to draw this thing at our breakpoint over here at 2, 3x minus 2 is, of course, a graph going up, and it's got a y-intercept of negative 2. And at 2, we already know it's up here at 4. So, you know, it's like this line right here. But we only use that equation to the left of 2. To the right of 2, we use this other equation, which is 4x plus 1. That's got a y-intercept of 1, but I can't graph it on this side because I'm only graphing it to the right of 2. I need to figure out where is this graph when x is 2. Well, 4 times 2 is 8, plus 1 is 9. So at 2, this thing is way up here at 9, and it's an open circle, by the way, because it's not or equal to, and it's got a slope of 4, so it's a little steeper than that other one. So there's a graph of your piecewise function, and you can see the limit as x approaches 2 of f of x equals does not exist, because the limit from the right is 9, because we plugged 2 into that equation for x is greater than 2. That's from the right. And from the left, the limit was 4. So therefore, this is not continuous at x equals 2. So here are some things. You might just want to take a screenshot of this page, but here's some things you need to check for discontinuities. Vertical asymptotes and holes and breaks in their graph. Holes are called removable discontinuities, and they are going to happen anytime in factored form when you get a common factor in the top and in the bottom. And that's going to be called a removable discontinuity. It's called removable because, watch this. We removed it. It's gone. See? That's a removable discontinuity, and we get a new function x plus 1. That's going to be a hole in the graph at 2. You've seen this before, by the way. That's not the first time we've talked about that. Now, vertical asymptotes are going to happen when in factored form, and after you take out anything that's removable, is if you still have something in the bottom that makes the denominator equal to 0, and it does not cancel anymore. So here, I would remove that discontinuity at 2x plus 1, because that's just a removable discontinuity. However, I still have at x equals 5 a place where I can make the denominator 0, and that's called a vertical asymptote, and that is non-removable. That is nothing you can do about that. The graph is either heading straight towards positive infinity or down towards negative infinity. That is called non-removable because I didn't have a common factor in the top and bottom. Breaks will typically almost always happen with piecewise functions, especially if those piecewise functions don't line up. For example, out here at 4, at that break of 4, 3x minus 1 is up here at 11, open circle, and it's got, that slope there. And this other graph, x squared at 4, is way up here at 16, and it's filled in, and it comes down here like this little x squared graph. That's really horrible, but you'll get over it. I hope you still love me. Okay, anyway, so that's typically when a break happens, especially if these y coordinates don't line up. And also on trig functions, anytime you have asymptotes, that function is not going to be continuous. Now, sine and cosine will always be continuous, but tangent, secant, cosecant, cotangent, anytime they have asymptotes, that's where it's not going to be continuous. All right, let's take a look at a couple of examples here, and let's classify some discontinuities. This top example factors into 2x plus 1 times 3x minus 4. And then the bottom one factors into 2x plus 1 times 4x minus 3. So let's talk about what we have here. This is discontinuous at 2 places. It's discontinuous at x equals negative 1/2 because negative 1/2 makes the bottom 0. It's also discontinuous at x equals 3/4 because x equals 3/4 also makes the bottom 0. Now let's be more specific, however. What kind of discontinuity is it? The 2x plus 1 factor that created the x equals negative 1/2 discontinuity is called a removable discontinuity. That means there's just a hole at negative 1/2. At x equals 3/4, however, because this does not cancel with the top, this is a non-removable. And what is that called again? That's called a vertical asymptote. Now let's take a look at this piecewise function here. When x is 5, 2x minus 1 is a straight line, and when x is 5, 2 times 5 is 10 minus 1 is 9, up here at 9, open circle up like this. And then when x squared minus 16, x is less than or equal to 5. If you plug in 5 for x, 5 squared is 25 minus 16 is 9. That means that it's meeting. They're actually matching up, and it's filling in that hole. This is a continuous function. Even though we had a piecewise function, it's still continuous. I want to show you how to input this on your TID3 or at TID4. I've got it in y equals here, you just put your function in parentheses, and then you also do parentheses x is less than or equal to 5. Your less than or equal to is right here in test. You'd have to hit second math to get there. You can see I've hit second math. And then the second equation is 2x minus 1 for x is greater than 5. And you can see that they meet up, and so it's not discontinuous. So you have to check and see if those y values are matching or not. And tangent of 2x is not continuous because it has vertical asymptotes. And where are those vertical asymptotes? Tangent has vertical asymptotes at pi over 2 and at negative pi over 2. I'll just find this first one here. This first one happens at pi over 4 for tangent of 2x. It's discontinuous there. And it's a non-removable discontinuity as well. Okay, so here's some things you need to know. Polynomial functions like x squared plus 5x or 6x cubed minus 5x squared plus 9x minus 3. Polynomials are always continuous everywhere. You don't have to check them at all. You're always continuous. Rational functions or fractions, they are continuous everywhere except when the bottom is equal to 0. So you got to check and see whether it's a whole or a vertical asymptote, but they will be only continuous. They'll be continuous everywhere except when the bottom is equal to 0. Radical functions, you have to figure out, they are continuous everywhere, but you have to set the what's inside the radical greater than 0. So if I had something like the square root of x plus 3, x would have to be larger than or equal to negative 3 because that's the first number that makes this inside here 0. And trig functions, sine and cosine are always continuous, but your other ones that have vertical asymptotes have discontinuities. So here's what you want to do when you're asked for discontinuities. You've got to find holes or discontinuous at that hole, but it's removable. And you do that by setting the bottom equal to 0 and see if there's a common factor in the top and bottom. For vertical asymptotes, you still factor and see when the bottom's 0, but you'll find out there won't be a common factor. Piecewise functions, kids really struggle with those. You just got to check the x values where the function breaks. So let's go through here. Is this function continuous? Yes, it's a polynomial. It's continuous everywhere. So this, I don't have to check anything. That's all I have to say. It is a polynomial. It's continuous. What about this next example? Is this continuous everywhere? No. I have to take the bottom and factor it. X plus 2, x minus 7. So this is not continuous at x equals 7 and at x equals negative 2. But I can be more specific and tell you what kind of discontinuity it is. At x equals 7, I have a removable. At x equals negative 2, this is not removable. And what is that called again? That is called a vertical asymptote. Okay, so I think we've seen enough of examples like that. So let's go for the last question here, and that is for this function, for what value of a is the function continuous? I've got a piecewise function. For this to be continuous, I need x squared plus 5 to have the same y value that 3ax does when x equals 5. It's because that's that break point. So I'm going to plug in 5 for x. And if I plug in 5 for x, I get that 30 is equal to 15a. And so that a value would have to be 2. And that's the answer to that. I know this has been a lot. So I hope you took good notes, and I will see you guys tomorrow.